For our project, we will be estimating oxygen diffusion in the retina through both Monte Carlo and using the equations learned in class. To talk about this, we must first explain what Monte Carlo is. Essentially, in Monte Carlo simulations, a large number of random inputs are used in order to understand the distribution of data. For example, if we didn't know the formula for the area of a circle, we could inscribe it within a square, which we know how to calculate the area for. We could then plot a large number of random points to find the ratio of the circle and square's area through seeing how many are contained within each shape, which allows us to estimate a formula to find the area of other circles. This approach is especially effective on applications such as diffusion problems, since while the general direction of particles is still known, as they move from areas with high to low concentration, there is still an element of randomness which fits well with how Monte Carlo works. Through inputting several random parameters, such as the particle distribution or direction, we can run the simulation with an extremely large number of particles in order to observe the behavior. This data can then be compared with the answers from our equation in order to see how close they are.
As Paul mentioned earlier, our Monte Carlo program will help simulate the Brownian motion of the particles. For our specific topic, literature has shown that a reasonable diffusion constant for oxygen diffusion in retinas is 1.97 times 10 to the negative 5 centimeters squared per second. To simplify our simulation, we are considering a one-dimensional diffusion through a slab of retinal tissue from left to right, or from high to low concentration. The basic algorithm works in the following way. First, for setup, 3,000 particles start initially near the leftmost end, where there is high concentration. Their exact position is randomized. Each particle then moves either left or right, since it is one-dimensional, by a total distance of epsilon equal to 1 times 10 to the negative 5 meters each time increment. The particles make these movements after each delta t, which is calculated to correlate it to the real time elapsed in the physical diffusion, which Jacob will elaborate more on. Then for boundary handling, the total length of the retinal tissue spans from x equals 0 to x equals L, where the left boundary is high concentration and the right boundary is low concentration. If a particle reaches the left boundary, it is bounced back and absorbed if it reaches the right boundary. The concentration of both must be maintained to simulate the flow from high to low concentration. This creates a steady state gradient. If we do nothing to the particles and let them flow freely, the flux will eventually be zero, but since we are artificially injecting and removing particles to maintain this concentration difference, there is a biased motion. Finally, for flux calculation, the simulated flux is determined by how many particles cross x equals L prime during a time interval.
To derive the time that we need to use for our Monte Carlo, we simply consider the mean square displacement of x squared. Firstly, assuming we move either plus or minus some step difference epsilon per step, we find that the mean square displacement of x squared is equal to epsilon squared per step. But from Fick's first law, we have the total displacement is 2 dt. Now, going to a total displacement rather than per step, we reach n epsilon squared, which is equal to t divided by our step time times epsilon squared. Equating the continuous and discrete displacement, we find that the step time must be equal to epsilon squared over 2d. Then, for approximating our stochastic error, first note that we may use the Poisson distribution, since our events are both independent and random. Letting r be the rate of events occurring, we start with the standard error of r being equal to the square root of the variance of r. But since n equals rt, we have that the variance of n is equal to t squared times the variance of r. So then the standard error of r is equal to the square root of the variance of n divided by t squared. But since we're using a Poisson distribution, this reduces to the standard error of r being the square root of r divided by t. Then using some basic dimensional analysis, we have to account for both area and Avogadro's number to relate to the standard error of flux, which we use to find that the standard error of flux is equal to 1 divided by a times n sub a, all times the square root of r divided by t.
In the first graph, we are comparing the position of the oxygen molecules versus the average concentration present in each of these regions. Once the steady state is reached, the theoretical distribution would equal the red curve that is characterized by the complementary error function, as calculated by Jacob. The blue points represent the average concentration from the simulation for each 2 times 10 to the negative 5th millimeter increment. In the second graph, we observe flux versus time, comparing two different methods of calculation. Flux is the rate of transport of a substance per unit area. The blue solid line shows the flux determined by the Monte Carlo simulation as a function of time. At t equals 0 seconds, we immediately see a drop from a very high flux rate, converging to the theoretical value we will get to next. Moving on to the theoretical value, the red dashed line represents the value calculated using Fick's law, which is then graphed as a constant value of 1.73 times 10 to the negative 5th. By looking at the two very different models plotted in the graph, we see the theoretical value that is calculated will always be the same, while the graph plotted using the Monte Carlo simulation shows how initially our graph starts with all the particles in high concentration, and there is an initial high flux value, but as the model continues running, creating the gradient, it begins lessening until it eventually converges to the theoretical value calculated by Fick's law.
Okay, so conservation of mass, right? Conservation of mass gives us the partial of the concentration partial time plus the gradient of flux equals 0, right? This is concentration of mass. But we also know that Fick's first law, right? Right, Fick's first law gives us that what? J equal to what? D, right, and C, right? This is what we're learning in class. But we plug this in, and we delta C over delta T equals, what is it? Nabla D, Nabla J. Well, this is D constant because I'll go ahead and turn myself. And then we have D, Nabla squared J. But 1 D can we have here, this simply, right, delta C over delta T is equal to D, delta squared C over delta and then X squared, right? And then this is our Fick's law. But now we're going to do this for specific boundary case, right? So we obviously have this. We also have the concentration at X, and the concentration of X and 0, for anything that's not the initial point is just 0, right? And the concentration at 0 and T is just our initial C naught, right? Because we maintain this concentration at the initial point, right? But we also have that as X approaches infinity, we want concentration to also run concentration point 0, right? This is where we get the semi-infinite case from, right? And we also know that X is similar to square root of dt, right? And this is just from, altogether, that's the Fick's first law. So we start with the conceptual method of similarity, where we get our eta, right? Looking for the f of eta, and we do this rule for solution, the concentration is C naught equals, well, what's this? D, C naught, F double prime of eta over D, and then T, right? So canceling, we end up with F double prime of eta plus eta over 2 times, right, eta 2 times F prime of eta equals Z, right? And then this is like ODE, pretty easy to solve, right? So now, just bring this over, and this ODE, I mean, method to solve, this is like really definitely trivial, but we do like we end up sending this eta to a 2 zeta, and then at the end of the day, we end up with F of eta equals the complementary error function of our zeta, right? So our final solution is C of xt equals C naught times the complementary error function of x over 2 the square root of dt, and then we're done.